And then we see what happens as we put conductance, as we put a voltage on this gate, measure conductance as a voltage on this gate near the bend, and we see a very, very strong response. Okay, so by putting a bend on the tube and putting a gate near the bend, we can locally tune conductance. It's like the bend makes a constriction, and then that gate opens and closes the constriction. So you can really, you can locally control your MOSFET type behavior. And there's physics behind this too. It turns out that when you bend a nanotube, you think of that crystal structure, you're making a local defect in that structure. So this is called a 5-7 defect, just add up the number of carbon atoms there. And it turns out this sort of defect is associated with p-n junctions in the tube. This has been well studied before, but it's sort of neat to see that this sort of p-n junction, it's like a diode, and it can be tuned with a gate voltage. Right? So now you can really study what's happening on the very physical level and what's happening in terms of what you can measure in these systems. Okay, what else? So now let's measure a voltage on a local gate at lower temperatures with no bends. We have a nanotube that's contacted and a gate over it. And we're going to see what happens to the conductance of the tube as we put a voltage on this gate. We're measuring at pretty low temperatures now. It's not in the Fabry-Perot regime, okay, higher temperature than that, but just conductance as we move this gate. And actually, it surprised me. The first time we did this, we saw these wiggles. Now, these weren't Fabry-Perot wiggles because they're not just continuous oscillations. We saw what looked more like steps. A step and a step and a step and a step and a step. And we studied this a lot and found that we always saw about 4 steps. And the separation between the steps was a unit of E squared over H. Right? This is just a fundamental unit. Right? It's not like a number 1.2 or something like that. It's a number that might be associated with some fundamental properties of the system. And it turns out, as I show you, it is associated with a fundamental property of 1D systems. So we saw what looked like these quantized conductance steps. And it's hard to see they look like steps here. You can look at it in a different way. This is a conductance plot. It's just high conductance is yellow and red, low conductance is black. And I just show you it to show that there really is a pattern of these steps. Right, you can see here that it sort of fits a pattern that you might expect here. And it turns out that these quantized conductance steps are actually expected in one-dimensional systems. It turns out that you can look at an equation for the current, and the energy dependence of the current drops out, and you expect quantized conductance steps in a one-dimensional system. So this is really one-dimensional physics that we're seeing here. It's because nanotubes are so small that they're quantized around the circumference, and yet you can get conductance through the length. And so only one, what you call quantum mode, one quantum mode, one wavelength, if you will, one wavelength of electron at a time gets through the nanotube, right? So first you have something that has an energy, just a wave like that, and then at a much higher energy you get another wave coming through. So these are the different electronic modes, one at a time, that go through the nanotube, and they're spaced by some known energy. That's the mode spacing. Okay. So it's really, really one-dimensional behavior. It's been predicted, but it wasn't really seen before in these systems. And this happens because our gate is just locally depleting carriers in the tube, creating a constriction that's allowing these modes through as we increase the gate voltage. And these things were interesting. It's pretty exciting to see it. They've been seen in some other systems, never before in a really 1D system. And they can be used to focus electrons. They have some spin dependence to them that you can study, to look at the degeneracy of the system, to study interactions. There's lots of things you can do to study with it. So we're still looking at this, trying to understand it. And one thing we're still really trying to understand is why we see spacing of just E squared on H. It should have 4 E squared on H spacing, but we see 1 E squared on H spacing, which looks like we're losing some of the degeneracy in our system. And we're not quite sure what's going on there, but it makes it really interesting to study. But in general, like I said, it's just, it's really purely 1D quantum phenomenon in this system. Okay, so here's the last example I'm going to go into of research that we've been doing on these systems. And that's the nanotubes. I've been talking about sort of 1D behavior in nanotubes. Now I'm going to move into what happens when you look at them as zero-dimensional systems. By 0D, I mean particles in a box. Okay, so from quantum mechanics, you know that if you confine particles to a small enough space, a box, right, they start obeying quantum mechanics. You get quantized energy levels there. And so if you consider a short section of a nanotube, the diameter is so small, even if it's sort of long enough to contact, it's still a pretty small box, right? The effective area is really tiny. So if you have sort of if you have weakly coupled source and drain leads, the nanotube itself acts like a box, and the electrons are the particles in this box. We also call these quantum dots, or artificial atoms, as I'll show. So now the nanotube itself acts like a quantum dot, where our gate is just a capacity-coupled gate that can tune the energy levels of this dot. You can think of it here, you get these quantized energy levels, right? And if your energy level is between the energy of the source and drain leads, you can get electrons going on and off your dot, your particle in a box. If your energy level is not between the source and drain leads, you get no conduction at all. So you get single electron conduction through this quantum dot, right? And you can see the energy level spacing is just particle in a box spacing because, and it's pretty big in this case. Okay, so if you look at conduction in this system, depending on where this energy level is tuned by the gate voltage. Depending on where this energy level is, you either get conduction of single electrons or no conduction. So you can see here, you get conduction showing a single electron is going onto your dot, then no conduction, then conduction again from a single electron. It's single electron transport. Right? You can think of it as a single electron transistor, or you can think of it as a way to approach single charge and spin control as well. So this in itself is it's sort of a cool system. People sometimes call these artificial atoms because adding single electrons, these energy levels, is like adding single electrons to the shells of an atom, right? So filling these energy levels is like filling atomic shells, and so it's in a solid state way of looking at atomic physics or at chemistry, physical chemistry. So this is well known. This quantum dot behavior has been known for 20 years now, but it hadn't been studied that much in nanotubes, and it was really hard to control this sort of behavior in tubes. It turns out that nanotubes make really good quantum dots. They're so small that you can see this quantized behavior at relatively high temperatures, higher than in other systems. They're pretty clean. You can make these just using standard lithography. And here are some examples of this single electron transport peaks, right? Each of these peaks is associated with a single electron coming on and off the nanotube. Okay, so before we started working on this, most people who made quantum dots in nanotubes just used the source and drain leads to define the dots. We wanted to make something more controllable, so we thought, why don't we use our local gates to define these dots in the nanotubes? The idea here is we put two gates on a tube. We deplete carriers beneath these gates, right? So there's no electrons here, and then the dot is going to be defined right between these two gates. So it's a very controllable way of making a confined region of electrons in nanotubes, a quantum dot. And you can see it here. Here's a long nanotube. Contacted off here, right? And then we have one gate defining one lead, another gate defining another lead, and then we put a local one in the middle just to tune the energy levels of that gate. As you can see, when we do that, we got a really nice controllable quantum dot here, right? These peaks, right? So we put this barrier at some potential, this barrier at some potential, tuned this middle gate, we call it the plunger, and we see that we get single electron conductance in a very, very controlled way in these nanotube devices. Okay, so why is this good? Well, it's good because if you can make one, you can make more. Right? So we're not, we can show that we can make one quantum dot in a nanotube. Why not make two or three? This is a scalable technique. So here you can see you can make a double quantum dot. Again, you have a source and a drain, right? And then you use gates to define two weakly coupled regions of electrons. And if a single quantum dot is an artificial atom, then a double quantum dot is an artificial molecule, right? You can control interactions, atomic interactions between this molecule. Look at bonding and anti-bonding states, all those things you might have heard from chemistry, you can actually look at and study now. Okay? And in this case, you only get conduction when the energy levels of both of these quantum dots line up. So if they both line up, you get conduction. If one of them doesn't line up between the source and the drain energies, you get no conduction at all. Okay. And so we've made these double quantum dots. We can make them in a couple ways. One is just, like I said, using lots of gates. You can see that here. These gates define each dot. The blue ones define the dots. The yellow ones tune the energies of each dot. We've also made it by just having a dot that having a nanotube that had a defect in it and tuning that defect. Right, so here's a defect and multiple gates, and it gave us independent control of the different regions of the dot.